Right, so this has been a fantastic conference. It's the first time I have been here, and it's just unfortunate for me that I can't stay any longer, but the talks have been really fantastic. The mix of talks has been really stimulating. And so what I want to talk about is some work that we did a few years ago, motivated by problems in statistical science. So, the first thing to say is that statistical methods are extremely important. Now, of course, I would say that being a statistician, but even in the Wall Street Journal, when the particular Hurricane Sandy was forecast to hit the seaboard of the US, then it was Monte Carlo methods that were used to help the decision makers and the policy makers in deciding where they would deploy or where best to deploy emergency resources. So it was very nice, again, as a statistician, to see in the Wall Street Journal mention of the Monte Carlo method. But I would say that in science and engineering in general, we are becoming more and more reliant upon a coherent and consistent definition and characterization of uncertainty. And of course, statistical inference within mathematical models that describe either physical or natural systems is becoming an area of research and an area of development that's becoming more and more important. And so quantifying and propagating uncertainty in these models is quite a challenge, in fact. And there are conferences, the SIAM conference on uncertainty quantification. There is a couple of international journals on uncertainty quantification. So this is a very important area. And it's a very important area of research that impinges on just about most subjects of interest. I've listed here from ecology all the way through to economics, from health science, medical sciences, through to the environmental sciences, and just about every aspect of the physical sciences and the engineering sciences is touched now with a great urgency regarding the quantification of uncertainty. And of course, the calculus that probability theory and statistical methods bring is the most natural one in characterizing uncertainty and subsequently propagating that. Despite this natural calculus, the actual mechanisms by which we characterize uncertainty due to induced probability measures, it turns out to be extremely challenging. And because of this, it is an area of very active research at the interface between applied mathematics and computational and theoretical statistics. And so what I want to do today is really focus on one particular area and one particular problem, and that is, how do we probe probability measures that are induced by the assimilation of observational data into mathematical models that describe some sort of phenomenon, either a physical phenomenon or a natural phenomenon. And I'm hopefully going to highlight why this is important, why it is challenging, and some of the open problems that certainly my group have tried to address, and why geometry should probably play an even bigger role than it has been. Let me just give you an example of a natural system. This was a very simple mathematical model developed by a mathematical biologist in Edinburgh in the 60s, Brian Goodwin. And what he was trying to do here was describe metabolic circadian control. So how metabolism follows the natural cycles of the circadian clock. And from a biological perspective, this is extremely crude. What the model describes is the production of some messenger RNA, which then is translated into a protein, and that protein is then translocated physically from the nucleus to somewhere else in the cell, which then inhibits the production of the messenger RNA that is producing it. So we have this feedback cycle, and the way that he modeled the translocation was just to insert a number of intermediate dummy proteins, if you will. And the kinetics of the production of the protein are just, the protein and the intermediate proteins are just described by these simple nonlinear and linear differential equations. And what they do is they define a dynamical system which induces a limit cycle. And so what I'm going to do is I'm just going to select the simplest possible realization of this model by having one intermediate protein. So we basically have this nonlinear system here of production and degradation. Again, production and degradation. And I'm going to pretend that I don't know two of the parameter values, so two of the rates of kinetic reaction. So they're going to be two unknowns. And I'm going to simulate data, right, in terms of the amount of protein that is actually measured at each time point. And what I'm going to do is I'm then going to induce a likelihood, right, so a simple probability measure on the likelihood of the data given this structural model and the value of the two parameters that I believe are unknown. And this is the probability measure that's induced. Okay? So in the two-dimensional space of parameter values, this is the measure that is induced. Now, one thing that you should notice about this is that there are an awful lot of morphological features in here which can be problematic. One thing that you can notice is that there seems to be a concentration of the measure in certain regions of the space, of the parameter space, and that concentration seems to follow some non-linear sort of substructure, so some kind of one-dimensional structure, if you will, in the two-dimensional space. And you can see that this concentration of measure is repeated. The reason for that, of course, is that there are many combinations of the two parameter values that would induce limit cycles which had comparable amplitude and frequency as the observed data. And you can see that these concentrated areas are also separated from each other by areas of very low measure, or low probability mass, if you will. And these are the combinations of parameter values that do not induce a limit cycle, and therefore are completely inconsistent with the cyclic data that we've observed. Now, statisticians typically would throw their hands up in horror and say, there's really not much we can do about this because it's not normally distributed. There are there's an awful lot of the mass that's distributed all over the place. What do we do with this? And the answer is, up until recently, not very much. And here are some Markov chains which were started at random locations and then run until basically they stopped. And the main point here is that, first of all, the local exploration of the Markov chains usually is concentrated on one of these areas where the measure is concentrated. You do not see any global movement at all because the Markov chain would take an potentially infinitely long amount of time to actually move from one ridge to the other. And so in terms of actually probing and exploring this probability measure, standard Markov chains pretty much fail. And if we want to compute important quantities of interest, like marginal likelihoods and so forth, then we are faced with an incredibly difficult problem here. And this is only in 2 dimensions, and this is with an extremely simple and almost trivial little model. Let's move on to something still pretty trivial. Let's look at an elliptic PDE that describes, in this case, steady state heat transfer. So this is very classical. And what we will be interested in is, given measurements of the temperature, we would like to infer what the values of the distributed thermal conductivity is throughout the domain of interest. Okay? So let's take a little domain which is just a heat sink, which is the sort of thing that we see in our GPU processors and so forth. And we're going to project the infinite dimensional field which describes the temperature distribution throughout the domain onto a finite representation using, in this case, a finite element mesh. And we will make measurements on the outside of the fins in this case. And the question then is, given the observed data, can we infer the values of the thermal conductivity in this material? Okay, well, we can just do a forward solve, nothing difficult about that. But what I'm going to do is I'm going to show you the probability distribution that's induced from this model given temperature measurements. And I'm just going to look at the distribution of the thermal conductivity at 2 points, right, at 2 endpoints of one of the edges of these 2-dimensional elements. Okay? Now, the reality is that we'd be looking at a 1024-dimensional object, but just to visualize and to understand the challenge that we're actually going to face, I'll just look at the marginal distribution of 2 values. And what's induced is something that looks like this. So again, what you can see is a concentration of the measure, and a concentration of the measure in some non-linear fashion. Okay? You can see this here. So, if you think of this whole space here, really all that we want to do is locate the probability mass in here, and then we want to be able to explore that in a statistically unbiased way. And the problem, again, similar to the first example, is this concentration and the fact that it's nonlinear. And so when we go up to 1,000 dimensions, we have these little shells, if you will, which are almost unconnected, where the mass is actually located. And so this is a very difficult problem from a statistical perspective. Let me just give you one final motivating example to give you further illustration of the challenge. I showed you the circadian clock model from the 60s by Brian Goodwin. Well, this is taking us up to date. This is one from the early 2000s. And there's much more detail in here. Proteins are translocated, within, into and out of the nucleus and into the cytoplasm and so forth. And the equations, well, the equations are not any more different from the kinetic rate equations that I showed you. First of all, these are just of simple Michaelis-Menten mass action type, but there's a few more of them. Now, the interesting thing is that if we try to explore the space of parameter values, again using Markov chains, then if we just look at the top surface, you can see that two of the dimensions seem to be able to be explored not terribly well, but the other four, the chain just doesn't move at all. The question is, why is this? Here's a little illustration to give some insight as to why this is actually a very difficult problem. I'm just going to show you 3 parameters of that particular model. And what you're seeing here is a Markov chain that's actually mixing, and the color values indicate the level of probability. So blue being small and red being high. Now what you see here in this probability distribution, if we look at this part here, we can see that the probability measure, the model that's inducing this measure, is completely insensitive to 2 of the parameter values and sensitive to only 1 of them. And then there seems to be some sort of phase transition, and all of a sudden, the 2 parameters that were completely insensitive are now extremely sensitive and driving the change in the probability measure. So being able to drive a Markov chain along or through a probability measure, right, where the sensitivity is changing depending on where you are in the space, is extremely challenging. And pretty much most computational statistical methods will fail and fail catastrophically in situations like this. And this is a very, very real problem. I was motivated to do the work that I'm about to talk to you about because I was working with cancer biologists who were studying far more complex systems than this here. And they were gathering lots of data, and they were wanting to test hypotheses about the structure of their models. So one model versus another model. And they wanted to use mathematical models and statistical techniques to test the plausibility of these. And so what I was trying to do was estimate what are called the Bayes factors, or the likelihood ratios, if you will, between one hypothesized structure and another, and estimating these in such a way so that they are biased and the variability of the estimates is sufficiently controlled to make sensible scientific statements was extremely challenging, especially when the laboratory was then going to invest a huge amount of money in doing experiments based on the inferences that we were making. So this really led me to consider it led me to start to look at the literature that you chaps and ladies produce. And we ended up publishing a paper a few years later, which was called Riemann. There's Bernard Riemann there. Manifold, little hyperbolic manifold. Langevin, naughty boy. We heard about him earlier on today with Marie Curie. William Hamilton, and the old casino in Monte Carlo. So we basically tried to capture as many, of the important mathematicians that we could. Fortunately, we got a Frenchman, a German, and an Irishman, but no Englishman. And so we published this paper, which basically described a way of getting around the problems that I have described to you, and opened up the door really for statisticians and computational statisticians to address much more effectively these types of problems. So the motivation was to improve stochastic search and stochastic simulation methods for these types of challenging problems. And the way that we did that is we explored some differential geometric ideas in devising MCMC, Markov Chain Monte Carlo methods. And the two things that we did is we looked at diffusions, so stochastic differential equations that would provide us with an invariant measure from which we could then use that SDE as a means of probing a probability measure, and defining these on a particular manifold. And then secondly, we actually looked at exploiting the notion of geodesic flows on that manifold as a means of creating a Markov transition kernel that would allow us to explore probability measures in very high dimensional spaces that suffered from this non-linear concentration of measure, which really defied most other sampling schemes at that time. And I'll give you some examples. So, Monte Carlo methods. In essence, if you're a statistician, whether you are a frequentist or a Bayesian, this is something that you will always do. You have some trial function, phi of theta, where theta is some random variable of interest, and you want to compute an integral with respect to some measure on the space theta. And the classical Monte Carlo scheme is to take the empirical distribution of the trial function, where the theta ends are draws from the distribution of interest, and we know that this will converge at a rate of 1 over root n, where n would be the number of samples used in our estimate that were drawn exactly from pi. The most generic way in which we can induce samples, theta n's, from a generic probability distribution is to define a Markov process which is ergodic and whose invariant distribution happens to be the target of interest. The way that this is done is that we can construct, there are a number of ways that we can do this. The one I'm going to focus on is defining a reversible Markov process. We construct a transition kernel which is made of two parts. The first part is that we have a potentially arbitrary mechanism to move from one point in the configuration space to another, so to perturb the location of our little particle, say, and associated with that would be some probability distribution, so P sub P, the proposal probability. Now, because this could be potentially arbitrary, and it's not the probability distribution that we're interested in, we would be interested in pi, then this sequence of perturbations will be biased. And so the way that we can correct for this bias is to include a probability of acceptance of the perturbation from theta to theta prime. And the way that this acceptance probability is defined is it's just the minimum of either 1 or the ratio of the target distribution at the new point versus the target distribution of the old point. And that is scaled by the ratio of the forward and backward probabilities associated with the proposal distribution. And taking both the proposal distribution and the acceptance probability in product form then gives us the definition of a Markov transition kernel whose invariant distribution would be the target of interest, pi of theta. Now, this is great. It's extremely flexible. But the rate of convergence of the chain to the target pi of theta and the asymptotic variance of our Monte Carlo estimate is pretty much dependent on our choice of this proposal distribution. So whilst in theory the correctness of the Markov chain is guaranteed by any arbitrary measure, probability measure, P sub P, clearly the efficiency of that process is going to also be governed by how far or how misspecified this proposal is from the actual target. And so there's been a huge amount of work in looking at how one would design the proposal mechanism. And there has been very little work until what we came up with on actually looking at or exploiting some differential geometric ideas in the design of this proposal mechanism. So I can skip over this, and I cut out quite a number of slides. I have to give a lot of differential geometry 101 material when I'm speaking with statisticians, but I think today I can just get to the meat of the talk. So because we're going to be considering statistical models, then one object that is of foundational importance for a number of reasons in statistical modeling and subsequent inference with these models is the Fisher information. And we've seen the Fisher information, or we've seen the Fisher metric a number of times in talks today. And I'm going to say that for some statistical model which induces a likelihood, so the log of the probability of data given model parameters, calligraphic L, theta, the Fisher information, G of theta, is just the covariance of the score function. So the derivative with respect to the parameters of the log of the probability of the data given the model parameters. So a classical measure of a bound on the variance, of the achievable variance on estimates from a statistical model. I want to go right back to 1945 to a paper that C.R. Rao published entitled The Difference, or Measuring the Difference Between Populations. And he was trying to understand how can we obtain an indication as to the distance between two populations that are characterized by a probability distribution. And so what he came up with was this chi-squared distance between a probability distribution of some data y under some model with parameters theta, and then a delta perturbation of the model parameters. So to first order, if we expand this to first order, then we get this bilinear form here, where the Fisher information matrix now provides the weighting of this inner product. And Rao understood that what this, by the definition of the Fisher information matrix, then what the Fisher information matrix is doing is inducing a Riemannian metric structure on the space of probability distributions. Interestingly, and for historical reasons, Jeffreys, a few years later, looked at this entropic measure, which gave the exact same notion to first order. And of course, people like Amari and the Japanese school have developed the whole idea of information geometry based on these divergence-based links to the actual geometry that's induced. So this was interesting because it meant that we now had a non-Euclidean geometry for probability measures, probability distributions, and so all of the beautiful concepts such as connections and geodesics, notions of curvatures and so forth, could all now be employed by statisticians. And that was done, but primarily in the likelihood framework for higher order statistical analysis of the efficiency of likelihood-based estimators. And there has been a rather long and illustrious history of work in this vein. I think another one which is very much related to this conference here is the whole notion of statistical shape analysis, image analysis, and so forth. So people like Kent and Kanti-Mardia did some work, and this is all now used in computer graphics. But the question that we asked was, well, can this geometric structure, can it be employed in Monte Carlo methodology to address the problems that we are facing? And the answer is yes. Now, I normally give this slide to statisticians just to calm them down so that they don't think they're going to get a whole talk on fiber bundles and cotangent spaces and so forth. Really, the machinery, the only machinery that we're going to use is basically just the Fisher-Rao metric structure, the metric connection, and the notion of geodesics. And again, I don't need to labor the point to this particular community. The Fisher-Rao metric is, of course, the natural metric as far as statistical models are concerned. The question might arise, well, are there others and other geometries that might be appropriate for specific tasks? I'm just going to focus on Fisher-Rao. And I'm going to give some examples just to kind of illustrate some of the points. Let's just take a one-dimensional normal distribution, a Gaussian distribution, that has two parameters, mu and sigma. The metric induced over the two parameters looks like this natural diagonal structure. Components of the connection just follow through with schoolboy algebra. And the overall metric turns out to be something like this, which I'm sure you'll all recognize as inducing a hyperbolic space. So in other words, univariate normal distributions, are the natural space, the natural manifold structure for them is the hyperbolic upper half plane. And so if I just consider four densities with mean and variance defined in this way, what we would typically, or certainly statisticians would typically think of, is that that these four normal distributions, are all separated, if you will, in this manner here, just by using Euclidean metrics on that upper half plane. Of course, the reality is the hyperbolic space looks something more like this, where normal distributions that have got larger variances are in an information theoretic perspective actually closer and more similar than those that have got smaller variances. And so this makes an awful lot of sense. But how is that going to help us in designing Monte Carlo methods? I love Escher's work describing. Of course, he wasn't describing a hyperbolic space there. I think he just liked this. He didn't know anything about hyperbolic spaces. Okay, so how can we just take this very simple machinery and use it to design a proposal mechanism that hopefully will be adaptive to the local geometry of the family of distributions that we're interested in? Well, one of the most obvious things that we can do is we can take an overdamped Langevin diffusion, okay, on RD, and if here's the Langevin diffusion. It has gradient of some potential function defining the drift, and then we have standardized Brownian motion in d dimensions. And we know that the solution to this has an invariant distribution, which is going to be equal to the exponential of the negative of the potential function. So what that means then is that if we chose a distribution or a distribution with respect to a Lebesgue measure that has Lebesgue density pi, and we defined the potential function for the Langevin diffusion as the log of this desired distribution of interest, and plugged it in here, then the invariant distribution associated with this diffusion would have Lebesgue density pi theta. So, if we use some numerical integration scheme, Euler-Maruyama I'm just showing here, but we could use higher order converging numerical integrators. So here is Euler-Maruyama, which describes the evolution of theta. We're now driven by an isotropic spherical Gaussian, Z. What we can look at is we can say, well, this actually defines a proposal mechanism in that we have our current state, right, of the configuration space theta, and we're going to make a perturbation to tau plus epsilon, and that perturbation is going to be driven by this deterministic component, right, which is the gradient of the log target, and then this diffusion term here. And the distribution, so if we take this, then what this mechanism does, what this discretized Langevin over damped diffusion gives us is a proposal mechanism which is a normal distribution over theta prime, whose mean is then just this term here, and the covariance structure is then just going to be the identity and scaled by the step size of the integrator. And we can then correct this proposal mechanism for the bias that it would introduce by the ratio of our target distribution. And that will define a Markov transition kernel which is invariant to pi theta. So this gives us one way of exploiting gradient information, if you will. The problem is what? Well, the problem here is that the covariance structure, the diffusion structure, is isotropic. And the examples which I've shown you, right, the real examples, if you will, not one of them is isotropic by any stretch of the imagination. Look at this here. So for us to be able to have a diffusion process that would have a high rate of acceptance probability, then the step size would have to be very small. And if the step size is very small, then it's going to be very, very inefficient in exploring this concentrated measure. So this is a major problem. The way that we get round that, well, there's been a number of ways of getting round that to do with adaptation and so forth. But in my view, I think the most beautiful and most elegant way of doing it is to exploit the underlying geometry of the statistical model and the geometry that is local. And so what we can do, from a numerical perspective, we can precondition, of course, and the preconditioned Langevin diffusion will still maintain pi as invariant. But the question then is, well, how do we select M, and how do we do it in a systematic way, and how do we do it in a coordinate-based way? The natural thing to do, and I'm sure you all thought about this immediately, was to define this overdamped diffusion and define it on the natural manifold for the objects of interest, which are these probability distributions. So if we then take the Fisher-Rao metric and the Levi-Civita connection, so we can basically start off with the Laplace-Beltrami operator in defining the generator for this diffusion. We end up with a diffusion on the manifold defined implicitly by this metric and the associated connection. And the diffusion now looks like this. And this diffusion, again, will keep pi as invariant. So now you can see a number of differences from this diffusion, which is defined on RD. And this diffusion is now defined on the manifold in RD. So the first thing you notice is that the potential function is now, it's preconditioned, but it's preconditioned by the inverse of the metric tensor. This looks very natural, because now what we're doing is we are rescaling locally around the point theta, so that basically the coordinates are all isotropic, if you will. And then here, again, the isotropic Brownian motion is now being scaled by the square root of the inverse of the Fisher-Rao matrix. In other words, the coordinate system is being stretched and squeezed and rotated to reflect the local covariance structure induced by the statistical model, and doing it at each point and doing it automatically. And this second term just comes from the fact that the curvature in the manifold is changing. It comes from the Laplace-Beltrami generator. So again, if we just discretize this and use it to induce a proposal mechanism similar to what we did previously, now we see that the gradient is going to be scaled appropriately, and likewise the diffusion term is going to be scaled appropriately. So the problems that we were facing with regards to how do we select the preconditioning have completely disappeared, because we have the most natural form of preconditioning of the diffusion, both the drift term and the diffusion term. And we're doing that at every point in the space. So we're not relying on some global averaged preconditioning. This is absolutely local and absolutely point specific, location specific. So again, we induce a proposal mechanism defined by this Gaussian distribution, which has mean based on this, and the covariance structure now you see is scaled not only by the step size, but it's also rotated and compressed and stretched and so forth by the inverse of the square root of the inverse of the Fisher-Rao metric. So we've got a proposal that approximately diffuses along the appropriate manifold. Here is a target distribution of Gaussian with a particular mean and a particular variance. And what we're going to do is we're going to set off a Langevin diffusion, and we're going to see, firstly, how long does it take to converge to the target, and then how efficiently does it sample that target. If we use the diffusion defined in RD and completely neglect the local geometric structure, then we get something that looks like this. This is great, but then this is a trivial problem. But you can see on average, an average step size of the chain. You can see it converges, and then once it converges, it starts to sample reasonably well. If we exploit the geometry of the manifold, then what we see is that despite these being uniform step sizes, we now make very large steps here because of the information associated with the metric structure. We converge much more rapidly. And what we'll see when we go to very high dimensions, that in actual fact, we can get almost independent sampling. So we can make very large steps that are still accepted. Why? Because we have information about the underlying geometry associated with these probability measures. So this is nice. Here's another example where we don't exploit the metric structure. You can see this overshooting and then very, very small step size required. Whereas here, very natural path that's being followed. And you can see how this is following the hyperbolic trajectories, if you will. And then very rapid convergence and then very dense sampling of the target. So this looks fantastic. And I'm going to reserve illustration of the method until I describe the second thing. How long do I have to talk, incidentally? 10 minutes, perfect. This was basically a first-order diffusion, a reversible first-order diffusion. I'm going to introduce you to a second-order non-reversible diffusion. So here it is here, okay? And of course this can be written in terms of, in this case, location and velocity. And so what we have is the, if you think of this, dv by dt and gamma. So gamma is basically just, so this is basically just the covariant time derivative of the velocity. Again, we have this term dealing with the fact that we're working on a manifold. This is a viscosity term, and I'm just saying that it's a unit viscosity term. And then we have a diffusion term. So this is defining the acceleration of a particle across a manifold and under the influence of a particular potential field, this potential here. Now, the question is, what has this got to do with MCMC? Well, it turns out, if we look at the Fokker-Planck equation, we can see that the joint distribution, so the invariant distribution of that diffusion on location and velocity takes this form here. So you can see that we've got a quadratic form, and then we've got the potential function. And if we denote the potential function in terms of the log of whatever target distribution we would like to sample from, and then this here is basically just the change from Lebesgue measure to Hausdorff measure on the manifold. If we plug this in, then it turns out that the marginal distribution for P of x is indeed the distribution that we want. So using the second order diffusion, we can target our pi of x in some sense. Now, I've looked at the configuration space. The more natural space to work in, of course, would be the phase space, where we're looking at location and momentum. Again, the results basically hold. So we're working in the cotangent space here, and so the natural symplectic forms emerge. But what you should be able to see here is that this system of ODEs, if I just look at this deterministic component, then this is basically a Hamiltonian acting under this particular potential function and defined on the manifold whose metric is G. The stochastic term, this one here, is basically just a conditional Ornstein-Uhlenbeck process. And so what we can do is we can use something like Lie-Trotter numerical splitting and split in terms of the deterministic Hamiltonian and use numerical methods to solve that. And then the stochastic component is driven by this Ornstein-Uhlenbeck process. And the two together will define a proposal mechanism when corrected with an acceptance probability, in the discrete case, will preserve pi of x as its invariant. And I guess I don't need to labor this point, but the proposals will actually follow the local geodesics on the manifold, because the geodesic equations can be written in terms of Hamiltonians. And in the presence of a particular potential field, then we're really dealing with local geodesics. And I don't need to go through all of this. I think you're all familiar with this. This is just for my statistics colleagues. So again, I don't need to go through all of this. This is the Maupertuis principle, which shows us how following the Hamiltonian dynamics also induces the local manifold geodesics. So this is great. We need symplectic integrators. We need symplectic integrators that are semi-explicit, because the Hamiltonian system, the deterministic Hamiltonian system, is non-separable. But these are all details. Let me just show you a quick example. A two-dimensional Gaussian with a covariance structure which is like 0.98. So in other words, we're looking at basically a very, very thin pencil in this two-dimensional space. Standard simulation methods using Gibbs sampling. Here are the traces. You can see that this is definitely not an ergodic process, and the level of autocorrelation from point to point is extremely high, which basically means that any Monte Carlo estimate would be pretty much useless using something like this. On the other hand, if we employ the non-reversible second-order diffusion, in other words, using the Hamiltonian dynamics on the manifold of probability distributions and using this conditional Ornstein-Uhlenbeck process, then we get almost independent sampling. very beautifully. If I look at another example, this kind of warped Gaussian, you can see that if we exploit the Riemannian structure, we really follow the natural contours of the concentration beautifully. I've got a number of other examples, but let me just... so this is a very challenging example, one because it's extremely high dimensional. So we're trying to sample a field, and in essence what we have is a statistical model which posits a latent Gaussian field which induces a mean function of a Poisson process. So the data that we observe are the counts of some process in a particular location in this domain here. So the incidence of the number of incidences of lung cancer in a particular region or what have you, or the number of green-eyed toads that were found in a forest, whatever. What we want to do is we want to induce the latent field, and we want to do this in a way that we basically want to sample this discrete field. And most methods, even using Langevin diffusions, just completely fail, catastrophically. I mean, you can see that, with the metropolis-adjusted Langevin algorithm, in the transient phase of the Markov chain, it needs to be tuned, and then once it reaches the stationary phase, it doesn't move, and so it needs to be retuned. It's just a total mess. If we exploit the natural Riemannian structure and use the geodesics induced by the Hamiltonian system, we get almost independent sampling. It's beautiful. And such a high-dimensional problem. And if I just show you the effective number of independent samples induced from 5,000 samples, typically using Mala, between 8 and 16 can be considered independent. So extremely inefficient. If we use the Riemannian structure with the Hamiltonian dynamics, we're almost getting independent sampling. It was quite remarkable. So this work has now been used by engineers and many other people. If I just take you to this example here, the heat sink, this is all the details. But in essence, what we get is independent sampling in that 1024 dimensional space. Quite remarkable. And there's been other applications in the medical sciences. This was a really nice example of a whole heart model, and what they were trying to do was infer the uncertainty in predictions based on the model. And again, they were what they did is they exploited the Riemannian manifold Langevin type schemes to sample from these sorts of very complex models. So let me just conclude by saying that statisticians have played about with differential geometry in characterizing higher order efficiencies of statistical estimators for some time. They were in the vanguard of statistical shape analysis and so forth. And now computational statisticians have a whole new tool set by exploiting very simple differential geometric notions. I mentioned the diffusions that respect the structure and the curvature of the space. I described how geodesic flows are used, and I've shown you how it works well on the sort of typical contemporary challenging problems that statisticians and applied mathematicians and computer scientists are facing. So it's very promising. The sort of ongoing developments, there's theoretical analysis, there's generalizations of this work to symmetric spaces, and one of my students is currently working on that with Tony Kennedy. Looking at geometries that are induced not by likelihoods but by Stein discrepancies. using Stein operators, and therefore would induce different manifold structures. And on it goes. There's lots of ongoing work, both at the theoretical and the abstract level, and also at the methodological, numerical level, as well as the application level. But what I want to leave you with is that I'm not for 1 minute saying that we've solved all the problems of computational statistics. We certainly haven't. But I think that introducing the power of differential geometry into the Monte Carlo toolkit is a very positive one. And here are some just recent papers of work that my group have been involved with in developing the basic ideas that I've tried to explain to you today. So thanks very much. I think there's probably a meal for you, so I don't want to keep you back from it much longer.
Thank you, Professor Girolami. Question?
Thank you. So one of the advantages of using a differentiable manifold model for the family probability density functions is that you are able to use the volume density to characterize how many discriminable models are at each parameter location, right? So now in this setting, when you have the Hamiltonian Monte Carlo, you use the symplectic volume density, whereas in the Riemannian case, I saw that you use the Riemannian volume form, right? So you have the square root of the determinant of the G, which is the Riemannian volume. So I want you to give some comments as to whether choosing different kinds of volume forms, what are their effects on the methodology and the simulation?
Yes, so that's a very good question. So the question was, what is the impact of the choice of volume forms? So first of all, our choice of volume form for the diffusion is pretty much defined because we needed that particular form to ensure that the invariant measure that we were interested in remained invariant. The dynamics in the Hamiltonian then is defined on a completely different space. It's defined on the 2D space rather than the d-dimensional space, so the volume forms will be different. So I've taken a very pragmatic view of ensuring that both the dynamics in the Hamiltonian case and the diffusion in the Langevin case, they both preserve, they preserve the measure that I was interested in. Now, questions as to, well, perhaps we could still use different types of forms, volume forms, and preserve that measure. It's something that I certainly haven't looked at. Alessandro, I think that might be an interesting question for you at some point. Good question. So it's really been driven by ensuring that the dynamics and the diffusions, had invariant measures, which were the ones that we wanted.
For the implementation part, when you have this matrix G to be inversed, for the low dimensional case is okay. So the number of the samples that you are generating to arrive at the convergence is very, very low, but the cost of the computation may be very high for each.
Yes. Yes. So this gentleman recognized the fact that there was an inverse of a matrix which could be potentially very high dimensional appearing in there, of which I made no mention at all. And so clearly solving a linear system like that is, in the naive case, going to scale as order d or order n cubed. And there's really no way of getting around that. So if the metric tensor induces a dense Fisher-Rao matrix, then there's not much that we can do apart from using nice numerical tricks. What we have done, however, is we have used emulators. So you know, the natural metric structure would be the full Fisher-Rao, but there's no reason to use an emulated structure that still captures, you know, some of the micro-scale structure that we need to exploit, and in which case actually using a sparse form is something. But that's, you know, it's numerical, it's very ad hoc, it's very application specific.
Yeah,
There's nothing free in this world.
but we, during the conference, we have a talk of Yann Olivier, who have introduced a method to when you have a very high dimension of Fisher matrix there is some solution also in the case of high dimension.
Good.
Yeah.
Excellent.
So I invite you to read the paper of Yann Olivier because it gives
will.
reference to your paper, and
Great.
he has introduced a natural Langevin gradients, and it's very close to your approach, and he also deals with high dimension for neural networks, applying this kind of strategy.
And this is where it would be very useful. Yeah.
Other question?
Sure.
Yes, thank you. You talked at the beginning of your talk about the Fisher-Rao metric, and then the description that you actually choose a family of probability density because of that you need dominating measure. And the second condition, silently, you do not say that usually you assume that density function is positive, or at least almost everywhere positive, right? To define the log and the derivative of log function. And then you define Fisher-Rao metric. But I just want to make a short comment that in our book, Information Geometry, just recently published with Lorenz Schwarzhofer, Jürgen Jost, and Nihat A. And then based our paper only will be accepted in Bernoulli journal. Then we remove all these conditions. That's the identness, that's the Fisher-Rao metric defined on the family, even not smooth family. I mean, that's we define on the parameterized family of the arbitrary, possibly infinite dimensional probability measure, not necessarily dominated measure. And therefore, identness density function, and therefore, identness positivity of density function. Yes. Everything. I mean, that's
I'd love to read that paper. It would be great if you.
Yeah. So that means that's on the condition for the Fisher-Rao metric. You can remove completely. Yeah.
I'd love to see that.
Yeah. So that you can do my talk about.
Thank you. I propose to close the session now because we have a last session and we are late. Very thanks to Professor Girolami